Hello folks, this is the second of the video series that I'm doing on buckling. And the first one was called Tutorial 4, and it's a warm-up for the present tutorial, although these can be treated independently, but I decided to do it in this manner so that no one video becomes very long. Now, a, a common question when people are doing buckling analysis with finite element packages, and I'm talking about the novice, is the fact that when they have several loads acting on the same problem, on the same part, and they want to do buckling analysis, they may decide to include all these loads in the same buckling step, and then once they get the result, they try to interpret the answer. So this is why it is very common questions like this arise. For a buckling analysis, must all forces be multiplied by the resulting buckling factor? Okay, and here's another one. I would like to do a buckling analysis with an additional fixed known lateral force. Okay, what should I do essentially? So uh, the reason that there is a source of confusion in this topic on this particular issue is that when the concept is introduced to them as an undergraduate, there's only single load acting, and they're usually introduced in the context of the Euler buckling problem, which is shown here. But there's only a single load that is acting. So in tutorial 4, I did this problem, and there was a single force that was downward acting, compressing the beam. Okay, and there was a single force acting. So in the buckling step, I did not have any other force showing up. There was only a single lateral force acting. And of course, the theoretical solution is something along this line. And uh, I used the linear three-dimensional elements, but I did introduce some restraints so that it essentially converted it to a two-dimensional problem. Okay, and I did actually the fixed free problem. I didn't want to use a complicated geometry because that masks the issue, and you spend a lot of time creating the model, but the basic question is not answered. Now, here, and I mentioned that if you get the buckling load, such as what you see up here, and you apply it to the bar as a compressive load and do a linear analysis, you won't see any buckling effect. You won't see any buckling. In spite of the fact that the load may be equal to critical load or even higher, you just see a compression of that. The reason is that all this stuff is assuming that the problem is perfect. In other words, there is no eccentricity of the load. The load is kind of in the direction of the line. There is no imperfection in the geometry. The geometry, for example, is always a circle of the same radius. But this is impossible for manufacturing purposes. This assumption is impossible. Or there may be lateral force acting because maybe there's a wind load here. This is a particular column in a structure. There's weight on top of it, and then there's a lateral force. So what I said is that we really need to introduce a lateral force. So I am going to introduce a lateral force here. So for example, 1 Newton downward, 1 Newton sideways. And I put it in the same buckling step. And I'll show you what the issue is when you do something like that. You got to be very careful because you get numbers. But the question is, what are those numbers? In other words, that number that I get as a multiplier, should I take the value of this lateral load and multiply it by that number, and this axial force and multiply it by, by that number? That's the same question that was raised by some YouTubers in the first slide. Okay. Now, first of all, if you do as I did in tutorial 4, a single 1 Newton load downward, you will get a buckling factor of 5.004. So the load is actually, the Euler buckling load is actually almost 5 million, which pretty much perfectly matches the Euler buckling load. Now, what if I apply a, a sideways load of 1 Newton. Okay, you apply a sideways load of 1 Newton and put both of these in the same buckling step, you're going to see, okay, the buckling load instead of 5.004 e to the 6 is 4.993 e to the 6. And you might say, okay, well, it's almost the same thing. And I show you that what if you do 10 or 100 lateral load, Newton lateral load, or what if you do actually million? This is 100,000 lateral load. Look at what happens to the the multiplying factor. Okay, so in this particular problem, you may be tempted to say, okay, well, this cannot be right, etc. So you can fix it, but generally speaking, when you have multiple load and not in a very simple way acting on a structure, you have to be very careful about putting these loads in the same buckling step. In fact, that is not correct, but we'll get to that in tutorial 6 though, okay? So what I have done here, just to show you, I put a lateral load of 0, 1, 10, and I showed you 1, and I showed you 100,000, and I got the values for uh, the, uh, the multiplier right here. You can see that. And notice that even when the load is around, for example, 100 Newton, these numbers don't change that much, okay? But when you go and put a load of 100,000, the multiplier completely changes, okay? We're going to discuss this thing in tutorial 6 a bit more, but here's the situation. So this is the same information displayed graphically for you. The horizontal axis is the lateral force, which means the first column, and the vertical axis is the axial force or the buckling load, okay? Now you can see that and this thing on the right side is pretty much the same thing on the left side, except that it's a zoomed in area, because here I've varied the load from 0 to a million, lateral load from 0 to a million. Here I go from 0 to no, 100. Okay, you can see that right there. Okay, so uh, yeah, I think there may be a problem with this particular row, but it gives you the message anyway what it should be. But there may be a problem with this particular number, because you can see that 100. I think this is a mistake. This 4.99 should actually be 1 point something. Let me go back here. That 4.99 should be that's for 1 Newton. Okay, so actually you can see that for 1 Newton is this, but this number 100 is completely different. This number 100, the buckling load due to 100 Newton lateral load is around 100 or something like that. Okay, good. But anyway, the point is that when you look at it, this is for 0 lateral load, which means the original buckling load. And then when you make the lateral load 1 Newton, well, the buckling load is very close to it. And when you make it 10, well, it's okay. It's not 499 or it's not 5. It's almost 4.3. It's this line. It's 10. And then when you go to 100, it's about 100. So this number is not right. This should be 1 or something. But anyway, so the question is, you have to be careful. The point is that you have to be careful on putting these things in the same load step, because here you might say, okay, if I put axial load, reference load of 1 Newton, well, maybe I should put an lateral load of 1 Newton too. Here it's not that bad, but there may be problem where that other load is not actually, it may be a pressure, or it may be, think about it as a temperature, thermal load, and you don't know what those relative things are. So it should not be placed in a same buckling load. I just want to go here. Yeah. So what I want to do in this particular tutorial 5, I'm going to do a problem where both of these are placed in the same buckling step. And then when we come back in tutorial 6, then we're going to do it properly. In other words, we put these loads that are known, or maybe they're intended to create an imperfection, is in an initial step, which is a static step, and then when it reaches the end, Then we apply buckling step, okay, etc. We'll do that in 6. But let's go ahead and do this problem for the case, for example, of a lateral load of 100 to convince you that actually this table is not quite right. When it's 100, it should be a different number, the number that's over here, okay. So let's go ahead and do this. We go to 3D Experience. Let me start with a part file. Now I can pull up the other example that I did, tutorial 4, and say we start here, but I'm not going to do that. These are simple problems. We can do it independently of each other. So let's go ahead and make a line. So under Essential, make a line, and the line is a point and direction. I want a point over here, which I don't have, so I'm going to create one. Coordinate 0, 0, 0. Okay, good. And the direction is direction Z, and the height is 100. Sorry, 1,000 millimeter, which means 1 meter. Okay, there we are. What do I do? Let's try it again. So point and direction, create this. Okay, and direction is direction Z. And over here, I put 1,000 millimeter and say, okay, there's my line. Now, the cross section is circular. I'm assuming it to be circular. That being the case, I don't need an orientation point. But if this was not circular, then you need an orientation point. I don't need it for the present problem. I can skip it, but I'll go ahead and do it anyway. So we create a point, and the point is, let's say 200 millimeter to the along the x direction. Once again, I don't need it for this problem. Actually, doesn't matter, but I wanted to put it in the x direction just to be like the previous tutorial. There, I don't need this, but I did. Okay, so let's apply the material. We're going to go to tools. Okay, material, add a material. I can use the same material that I had before, but I'll do another one. So I'll call it steel tutorial 5 December 25, Christmas Day 2023. Okay, all right. There it is, right here, steel tutorial 5 December 25, 2023. Apply to this, go through that, and it's going to be just straightforward steel. We're doing linear analysis. This is all linear, of course. So structural, abacus multiphysics, mechanical, elasticity, elastic, 200,000 MPa, 3 MPa, Poisson ratio 0.3. We don't need the Poisson ratio either, but we'll do it anyways. Okay, good. Now we're going to mesh this thing. So let's go ahead to structural model creation, empty FEM, and under mesh, I use a beam mesh, each one being 100 millimeters, so 10 elements along the length. I think we have it. Yep. And now for the cross section, we define the profile shape. So we go to properties, a 3D under this pull-up menu, beam profile. It's circular. I'll call it my circular section or profile, and it's going to be circular, and the radius is 60 millimeters. You say, oh, this should be semi-circular. Okay. Yeah, good. So there is a profile here created right there. Okay, good. And now we create the section, the actual section, beam section. So it says, what is the support? The support is right here. What is the profile? My circular section. Notice that I can close it without actually selecting the orientation point because it is circular, okay? But as I said, not needed. However, I can go ahead and select this. Actually, let's see, because let me check something here. Uh, Let me not select this and say okay. You see, the problem is that it even if I update, oh, it did take it. Okay, even cancel that. Even without selecting the orientation geometry, it actually accepted that. But some other software, I mean, if this was not circular, this would not have let me close this thing. But anyway, this is good. There's no problem. It's totally redundant. This point that I created was totally redundant for the circular cross section. Okay, let's go ahead and define a structural scenario, which means basically we're going to do a FEA model. So structural, and it is the model that I created. We say okay. Here is the red exclamation mark, no procedure selected. So I'm going to go here, and on the procedures tab, I'm going to select buckling. This is exactly what I did before, except that I had only one load later on. So we're using number of eigenvalues to be extracted is 10, and maximum number of iteration. If there is an error message saying that you don't have enough of them, we come back and change this thing. And it's a subspace iteration, which is default, good for small scale problems. Okay, good. So boundary conditions. So, I'm going to do boundary conditions, and let me see. Let me unpin these so that we can see these easier. So here, what is that? Boundary condition. We can do a clamp at the bottom, or we're going to do a fixed displacement. All 3 degrees of freedom, or 6 degrees of freedom, are fixed. So all 6 of them are fixed. That essentially becomes a clamp. And then this whole line will not go in the direction X. That's restricting it from being a three-dimensional problem. So we go to fixed displacement, that entire line, and no displacement in X, rotation up, rotation Y and Z are 0. This makes a two-dimensional problem. So, and the reason we do this is that in the 3D experiences version of Abacus, there is no element B21 for beam. There are no two-dimensional elements. There is B31, but B31, I want to turn it into B21, two-dimensional, so I just restrict the motion in direction X. Okay, good. So, and now we're going to apply our load. So under load, so force, this top one, at this top, I'm going to call this thing axial. Let me actually do lateral first, sorry. Let me do lateral. It makes no difference. Lateral force, 1 Newton. Oh, I said 100 newtons, right? I said 100. Okay, so in the direction Y, 100. Good, there we are. And another one in the direction Z, -1. And I'm going to call this thing axial force, compressive force. Axial compressive force. How about that? Compressive force. We say okay. And there we are. Now notice that both of these forces are placed in the same buckling step. I'm saying that this is not the proper way of doing it, because if this lateral load is known to us and it's not changing, it should not be placed inside of this box. It should have been done outside of that as a general static. Place the axial force in here. Good. And the reason I chose a 100 here, because I wanted to show you that there is a problem with this line. This should not be 4.99. So I just want to confirm that. Okay, good. That's pretty much it. Let's go ahead and save it. Okay, so let's do a model check. No issues here. Let's do simulation check. These are kind of equivalent to the data check in the Abacus CAE if you're used to that, to pick up trivial mistakes kind of done by the user. I don't anticipate any issues here. And we are extracting 10 eigenvalues. If we get an error message about the number of iteration, we go and change that default value of 30 iterations to 100 or something along that line. This is fine. And now we're going to run it. And what we should do is we should get, once it runs, we should get a table like that, okay, except that these numbers, of course, are going to be different because we are applying 100 newtons. Those tables were corresponding 0 lateral load, 1 newton, and 100,000. And I did 100 because I want to show you there's a mistake in that table, in my table, Excel table. Okay, good. Right here, see, almost 100,000, right? This is almost 100,000. Actually, almost a million. Sorry, this is almost a million, and that shows you that this entry is not correct. This entry should be around 1 million. Okay, that's not correct. And close that, and you can look at displacement if you want. There you are. And I will not pursue this thing any further because I wanted to show you what does it mean when you say you put these things in the same buckling step, because we're going to do it differently later on. Now notice that, by the way, when I applied 0 lateral, obviously 1 Newton lateral load, 10 Newton lateral load, the numbers were not far off from that. But as you increase the lateral load, these numbers begin to change quite a bit. Okay, this one came out to be 1 million, typo here. Okay, 1 million, and yep. And in this particular problem, it's not hard to see there's something weird happening. But in general, if you have multiple load coming from different sources, pressure, temperature, gravity, etc., then one has to be careful. We can't set everything equal to 1 and then expect good answer. This is just sheer luck with a simple problem like that. Okay, one last thing before I forget. If you want to see, this is fine, there's nothing wrong with it, except that if you want to see the three-dimensional view of these things, which is just for visual purposes, double click on that, click on this tab, third tab, and instead of line, for example, you say uh, profile and say apply. You see the view like that. And if you want to see this, if you want to see just the no mesh, you don't want to see the mesh, apply. This is just for visual purposes, okay? It really means nothing. So I'm going to stop here, and in tutorial 6, we're going to repeat this kind of a problem, but we take the known lateral load and put it outside of the buckling step. All right, good luck.